Okay, welcome everyone. This is the presentation of the master thesis by Akshay Tiwari about deep learning applied to an environmental system. So Akshay, we expect from you around 20 minutes and then we will ask questions.
Okay, so should I start? Okay, cool. So hello everyone, my name is Akshay Tiwari and the title of my thesis is Applying Deep Learning to the Analysis and Modeling of Carbon Dioxide in a Particular Location in Balearic Island. My advisors are Dr. Manuel Matias and Dr. Iris Hendricks. So the problem was, which we already know, is carbon dioxide levels are increasing. It's quite twice as the pre-industrial levels. 26% of total carbon dioxide atmospheric is absorbed by the oceans, which in fact results in the imbalances in the ionic chemical balance of the ocean. This, which in turn leads to the ocean acidification because the pH decreases. And this is quite heightened in Mediterranean region. All the climate change and ocean acidification as compared to other places is quite high here. So it's very important to find the factors which affect this dissolved CO2 in the oceans. So the aim was to use deep learning to find all these factors which affect dissolved CO2. And deep learning was chosen because it's very dynamic in nature, which means that in the inputs which are provided to deep learning, even if they're changed or tweaked a little bit, it more or less can handle that. But deep learning requires huge data sets. So even before applying deep learning, you have to figure out how do we apply deep learning. So one of the methods for applying deep learning on this small ecological data set was transfer learning. First would be, let's say if you have one data set, fruits data set with input parameters as color, weight, height, species, and you have to predict the target parameter, which is the sugar content in it. So what you can do, rather than just using this data, you can ask for additional helping data sets, which is patient data set, in which you have heart rate, weight, height, cholesterol, health risk. So transfer learning says that you don't just have to use this data set, you can also use the patient's data set to say something about fruit data set because it has weight and height. The problem is weight and height of patient is not at all similar to weight and height of a fruit. But there is some relation between these two things because at the same time, they both represent at some general level, abstract level, the biological mass and height of a biological object. So you can learn something. So the idea of transfer learning, learn something from here and then apply it on the fruits data set. But since you're learning something here, you don't just have to learn from one data set. You can have multiple data sets. For example, you can have a flower data set which has color in it. So you can learn something about color and then apply it here. And your other data set, fruit data set, that's the main data set which you want to predict. That's only one. So this is the general idea of transfer learning, which is one of the methods which we'll be using. The other method is symbolic regression, which means that you just take a library of mathematical operators, you choose randomly from them and randomly form formulas out of it. You make formulas and then you predict whichever gives you least error. This is very simplistic because we don't you choose randomly. There are some generical algorithms behind them. But here we are not using generical algorithm, we'll be using deep learning with this. So that's the idea for symbolic regression. Since for transfer learning you need two data sets, main and the helping data set. The main data set is obtained from the Media Institute. It's at the Cap Salina. It's a cape at the southern tip of Mallorca. The values are bi-weekly. Every 2 weeks you get one row of data values. It's an in situ data, and there were some outliers for dissolved carbon dioxide which were removed by comparing with another data set called as Lampedusa, and the range is from 2006 to 21. And because of the removal of the outliers, the rows were reduced to 208. And helping data set, there were like three main helping data set which were obtained from Copernicus service. And since these are helping data set, they don't have to be similar, they don't have to follow any rule. So their temporal range is completely different, 12 to 18, 15, 20, etc. And they have mixed values, some satellite values, some in situ values. But these were restricted to Mediterranean region because I wanted to see like what happens if you just use Mediterranean Sea. I mean, you can extend it to other oceans also, but first let's see that. And it has some similar parameters like pressure, temperature, dissolved oxygen, chlorophyll. So first is the self-attention, which is a transfer learning method which we'll be using. So you take all the input parameters, you club them all together in one row, and then you pass it through the embedding layer. What embedding layer does is it converts each of the input parameter into a vector. So this vector, why do we do that? Because a three-dimensional vector will be much more capable of holding information, and it's much more expressive than just one scalar. But the moment you do that, you lose information about your input vector. So you have to add that input vector again, not adding, but concatenating. So you concatenate, and then you get this embedding layer. Each column represents one of your original input vector. So let's just see what happens. How do we perform self-attention on 4 of such input columns? You dissociate them into individual columns, call them A, B, C, D. And then you ask, because you want to find out the relationship between each of the column to other columns so that you can predict the target variable. You ask the question, how important is B for other columns? And then how important B for other columns in a three-dimensional space would be like how well aligned they are. The more aligned they are, the more important they are for each other. So you just take a dot product. Dot product tells you exactly that how aligned they are. And then dot product will give you a scalar. That scalar will show how much to scale each of these things to pass them on to the next layer. So the least important things will not be scaled at all, and they should not be passed to the next vector. So you scale them with the scalar which you obtained, and then you pass to the next layer. And that's the idea of self-attention layer. And it's not just that layer. So you take different helping data set, you take one row from each one of those data sets, and then you pass each row one by one first through an embedding layer, as explained earlier, then to a self-attention layer. You will see all these plus addition symbol all over these models, because that's what it happens. When you pass through a layer, you lose information about the original or the input. So you have to give it back to, these are called as rest nets. These are quite often used tricks in deep learning. So you pass it through the self-attention layer, you again add the original information, then you pass it through a layer norm. Layer norm is usually used to smooth out your lost surface. And then now this multi-layer perceptron layers, you pass them through multi-layer perceptron. So you dissociate each of these things into individual columns and then pass them. You're doing this process so that you give the model ability to so you give the model ability to change itself if it wants to change itself, because right now you're just multiplying and taking the dot product. So if you give the model the ability, it can change whenever it wants to tweak something on that vector. So again, because you have changed something, you again add the original input, again pass it through layer norm, and again a rest connection. In fact, initially this rest connection was not there, and this rest connection itself increased decreased the loss by 6 units. So it's quite useful to give these things. And this transformer block, this whole is called as a transformer block. It's just one small part of the whole transformer. So you take these input layers, you pass them through a transformer block, you get the same, you get a matrix which has the same shape. So you can again pass it through different transformer blocks, and then at the end of it, you take an average. So you get like one-dimensional vector, which we will call as internal representation. So you take that internal representation and concatenate with each of these input vectors. So you have one row, and then you attach the internal representation at the end of each of these rows, and then you feed it to your classifier, whose job is to predict your final target vector. So what you're trying to do here is you are trying to teach the model, no matter what input you give from which data set, it should be able to give you an internal representation, which is kind of an information which is helpful for these classifiers to predict that the things which you want to predict. The next approach is here. What you were doing is you were telling the model that, hey, this vector is oxygen, or this vector is something else. So the model has the ability to know that something about the input. But another approach is we don't want to tell anything to the model. We just want the model we can just show the different permutation and combination of these input parameters to the model, and then say that, hey, we are showing these parameters, we are showing these permutation, and it's your job to figure out. So we can extract all the permutation, but the problem permutation scale with n factorial. So we'll just restrict ourselves to all the permutation of length 2, 3, and 4, and not only all the permutation, just k number of permutation of length 2. So k can be, in the project it's 15 and 31, but here it's just shown to be 4. And then you apply 1D convolution. 1D convolution is just a linear layer, just like fully connected network, but just because it will be sliding on all the vectors to grab all the combination of these input parameters and the permutation of individual parameter, it's called as 1D con. And then it will give you a k dimensional output in each of these cases. Yeah, so this is the idea of permutation convolution layer. So you similarly, just like the self-attention, you take 3 rows or 4 rows or n number of nodes from your n data sets. Here's the difference between that method and this method, is that you take this and then you normalize it with normalize it column wise or row wise, which means that you take the biggest value in the column, smallest value in the column, and then you normalize it. So it gives the model idea where this value is respective to the biggest and the smallest value. So that's quite helpful for the model, and which you can do. And then you pass these through permutation con layer, like the earlier layer, and then you'll get like k groups, but there are like 3 things, 3 layers, a permutation combination of 2 length 3 and length 4. But each of these each of these con layers has it gives out 256 layer filters. So that's why you will have 256 into 3 here. But the problem now is that you have this represented AC near DE near CA, but this AC being near DE is just a coincidence. It's just the result of random sampling. You don't want this positional information to be learned by the model. So you have to collapse this dimension and increase the channel dimension. So that's why you apply stride to con, and then you collapse it, and then you get one single vector of this size. You pass it to multiple multi-layer perceptrons, so that you can reduce its size, and that's your internal representation. And again, just like the previous one, you take this internal representation, concat it at the end of inputs, and then give it to classifiers so that it can help them predict. The last method was the symbolic regression, the deep symbolic regression. The idea is like you can look at this formula and then you can convert this into this graph, because division will be the primary node, and then it has 2 children, log and sine. And so you can convert it into this graph and tree, and then from that tree you can convert it into a sequence. The sequence is converted by a rule called as pre-ordered traversal. So you go from left to right and then up to down, which means this thing will be the first division, will be the first operator in the sequence. And then you go from you have 2 branches. Which branch would you take as next? You go from left to right, so you take the left branch next, sine and x. So you go up and down in each branch, and then you go to the right one, log, and then multiplication, then x and x. So this is quite important, because then that's like saying that a formula is just equivalent to a sequence. We don't have any, in deep learning, we don't have any method to handle formulas, but we definitely have a method to handle sequences, which are RNNs and nowadays transformers. So what you do is you give empty tokens to your RNNs. The empty tokens say that indicate RNN that predict the first operator. The first operator, let's say RNN predicts division. And these 2 tokens, which are empty in the first place, the first token represents the parent. Like whatever the RNN is going to predict, this is the parent of that token, and this is the neighbor of that token. For example, this token predicts log. So log's parent is division. So log's parent is division. So division is given as an input, and sine is the neighbor of log. So this information is given to the RNN, and our RNN's task is to predict a sequence which we can then convert back into tree and then into a formula. So these were the explanation of method, and these are the results. I also threw in just one random vanilla neural network just to see how it performs compared to other. So in case of the model size, this is important if you want to do some real world application like online learning or something. So this is just a formula, so its size is not relevant. The biggest size model was Permutation Con. The number of training points, deep symbolic regression took more points to reach the same results as Selfattention and Permutation Con. The result, the errors were pretty much the same for all the models except for vanilla, which performs quite not that good, which is for obvious reasons. And these are the graphs which you can see. So if you focus on, these are the test data set. The red one is the actual values, and blue is the model prediction. So if you look for these 2012, 6th week of 2012, the error is huge, and that error is huge for all the models. So that means that all the models perform bad on certain values, and it's also true for certain other values. This may mean that these are outliers, and this may also mean that these values show that the models are learning correct things, because all the models are performing bad on these things. So this is not due to some artifact or some wrong layer or architecture in the model. This is due to the correct learning of the model, and these points are outliers. So because these points are, they are inherently difficult to predict. So this can also be a method to predict outliers. This was a formula given by the deep symbolic regression with these things, which are the biggest driving factor: temperature, dissolved carbon dioxide, atmospheric carbon dioxide, weak. Yeah, these 4 things. And with these constants, interestingly, yesterday I was searching these constants on the internet, and this constant appears a lot in drug trials. I don't know why, but so you can do one more thing. All the embeddings which you have in self-attention, you can take those 256 dimension embeddings and apply principal component analysis on it, reduce them to 3 dimension, and then plot them in a 3-dimension way. So when you plot them in 3 dimension, some of the parameters, they fall on a straight line, and when they fall on it, so this is from different angles, these parameters which are falling on the straight line, and these are the parameters which are falling in the straight line, just a zoomed in version. So all these parameters, they are NT, PT, phosphorus, and silicate. So the model grouped together all these things, all the nutrients together. It grouped together the chlorophyll, phytoplankton, and pH, all the biological stuff together, and CO2, dissolved CO2, atmosphere, which these are the 3 big drivers together also. And this was done by the model not even looking at the data set. It just learned everything from the helping data set and then predicted these things. You can also do the same with the internal representation. You can squish the internal representation to 3D and then plot them together. So once you do that, you find that the data set has been plotted into 2 planes. This first plane represents the values where the dissolved oxygen is 0, because in the data set some of the value dissolved oxygen, so it automatically separates the points where the dissolved oxygen is 0 from the points where it's not. So it divides it into 2 planes, and then if you look for the year 2020, the weak numbers, it has arranged these weak numbers on y-axis from right to left in an ascending order. So, and this was like this, all this the model grasped just by learning from the helping data set. It had never seen this data set on which it's predicting. And this is the same for the year 2013. So another thing is, like, you can take the atmospheric CO2 values less than 400 and see that all those values have been shoved to the right hand side, and all the CO2 values of the bigger than 400 have been shoved to left hand side. And similarly, if you look for the dissolved oxygen, there has been there's a small group of values for dissolved oxygen here. Why these things have been grouped together? Because they are less than 20? No, because there are some other values which are less than 20. But if you look here, these values have their weak, I mean, these are less than 20 and their weak number is also less than 11. So all these values which are less than 20, they correspond to other weak. So weak acts as an helping thing which helps model to differentiate between the similar dissolved oxygen. And this is just the same thing done with the internal representative permutation combination. It forms itself into a nice spiral. I couldn't understand why this was, because it just tells you that it's in spiral. More investigation is needed in that, but it may be due to the sinusoidal nature of the data set. So the conclusion is these are the 4 most important driving factors, and the transfer learning is working because it kind of grasps everything from the data which is unseen with the help of helping data set. DRS and self-attention can be used for online learning because they're so light. The values of some of so here you can use these models to predict CO2 dissolve for data set which doesn't have CO2 dissolve if you have some of the driving factors. These are effective for other smaller data sets too, because you can use for other because they're not specific to any data set. And these can predict with just 1 row. They don't need previous 5 or 6 rows. So that's also great. But you can try doing this. I mean, this can be done further to see how they react to by being fed by multiple rows. And self-attention permutation can be combined. That has to be investigated more. What's the meaning of that 3D spiral? And obviously an analysis of the formula generated by the DSR should be done, and more data set like these helping data sets were restricted to Mediterranean. Indian and Pacific Ocean can also be included and see how the results, do they improve or not. So that's it.
Thanks. So now it's our turn for questions.